Yes, thank you very much for the introduction. And this is joint work with my wonderful collaborators, Bobak Kiani, Hannah Lawrence, Stephanie Jagielka, and Melanie Weber from MIT, Harvard, and TUM. So I'll go a bit more slowly in the symmetries side of things, because I think that's the part where most people here are not super familiar with, and speed things up a bit in the learning theory frameworks. But as always, let me know if there are questions during or after the talk. We would love to be happy to chat with you about the work or related work. There are still lots of things to do in this space. And also, my co-author, Bobak, is also here in the conference, in the workshop, so feel free to catch him sometimes to ask questions as well. Right, so let's get started. So a large chunk of this line of research in machine learning that try to develop invariant or equivariant neural networks comes from a simple observations that a very specific machine learning task often manifests itself in terms of some kind of symmetries in the input domain. So what do I mean by that? For example, a very specific example, detecting the presence or absence of a number 7 in, let's say, MNIST data set. And well, a number 7, if you rotate it, is still a number 7. So these 3 images should be considered equivalent in the input space. And so this example also tells us that we should be a bit careful in designing the symmetries, because if, for example, we want to detect 6 versus 9, then rotation is no longer a good thing to do, because 6, if you rotate it 180 degrees, it becomes a 9, and vice versa. And also, if, for example, you want to detect 7 versus letter L, capital letter L, and you add in like reflection, then that's also not valid, because the middle image, if you reflect it, it becomes a capital L. Right? So there are nuances, there are complicated things to do in this kind of language of phrasing machine learning tasks as symmetries in the input space, and that's both a good thing and a bad thing. The good thing is that it tells us that this language of seeing things as equivalence classes is expressive enough to encode a lot of information about the task that we are trying to do. And the bad thing is, of course, if things are too complicated, then it's very hard to design, let's say, functions, neural networks that obeys all these symmetries. Right. So cleaner examples would be graphs. And graphs have a permutation invariant in structures in the nodes. So if you take all these nodes and you permute them, and also permute the corresponding edges, you end up with the same graphs. So all these 6 different objects, they look slightly different because they have different node labels, but they're actually the same graphs. One is always connected with 4, 2 with 4, 3 with 4, and nothing else. So they are the same object. For example, we point cloud, which is a set of points in 3D space. And together it represents some kind of objects in 3D space. Here's a kettle. There are 2 kinds of symmetries here. One is permutation invariance in the points. So the order in which you add points to this point cloud doesn't matter. In the end, you still get a kettle. And also 3D Euclidean actions like translations or reflections or rotations in 3D space still give you a kettle. And again, this can be also task specific, because if you want to design like a house safety system, you would want to distinguish between a kettle that is upside down versus a kettle that is right side up. Right? So we can encode many informations in terms of symmetries or equivalence classes in the input space. At a high level, what's happening is that there is a smaller effective domain. There's a distinction between what we input into a neural network. Usually this will be some kind of vector space. And we choose a vector space because it's convenient. You can store it efficiently in a computer. And also it's compatible with GPU learning, or these days TPU, or all this fancy stuff that we have. We want it to be some kind of matrix multiplication operations so that we can do backpropagations on the GPUs and enjoy all the scalings in the world. So there's a distinction between what we actually input into our neural network and what is the effective input domain with respect to the tasks that we have at hand. Right. To give very concrete examples, images are often stored as a tensor of pixel RGB values. There are 3 dimensions, one for width, another for height, and the third for the color channels. Well, in fact, if we know that the task, for example, detecting number 7 in an image is equivalent to is equivalent under rotation of images, then all these equivalence classes of rotated image should be considered the same. And any reasonable functions should output the same output when inputted a rotated version of an image. Right. Another examples, and what we usually do with graph in practice is that we input adjacency matrix, Laplacian, while we actually want to just represent graphs. So if you permute the rows and columns of an adjacency matrix with the same permutation, it should be the same object. And your function, the hypothesis, should be able to reflect that invariance. Okay. And for point clouds, what you have is what you represent in the computer is a tuple, another tuple of coordinates in 3D space. But what we want is some kind of object representations. And it's usually hard to put a kettle in a vector space and do linear algebra with kettles. Right. And our answers to input domain symmetries is not to go into the input domain and find these equivalence classes. In fact, we capture it through our models. For example, CNNs is built to capture translation invariant. If you loop your filters around, it's also cyclically translation invariant. GNNs, which I have not defined, but we'll see some example of GNNs a bit later. Our graph neural networks is designed to be node permutation invariant. So if you input a Laplacian adjacency matrix and you permute the rows and columns with the same permutation, it should output the same function. We want that guarantee. And if you're working with LLMs, for sometimes transformer has been used to represent sets, but just by ignoring positional encoding. So if you, for example, vision transformers, you look at patches in the image, and then you forget the relative positions of the patches with respect to one another. So what you end up with is a set of tokens, and being a set it's invariant to permutations of these tokens. So it's been used as a set function. So again, at a higher level, there is a smaller function space that contains the ground truth with respect to the task that we're interested in solving. We start with an input to the model, to a neural network model X, and we have some space Y that are labels. So this is a supervised learning setting. And in deep learning, we parameterize X, these functions from X to Y, let's say continuous functions with some bounded norm, as, let's say, neural networks. Well, if we have the task that at hand, there is a smaller input space, and with it, a smaller function space that will contain our ground truth functions, and we want to parameterize this space of function instead. Okay, so we have a smaller space of function, and conventional wisdom in computational learning theory would tell us that if you have a smaller function space in some notion of dimension, then it becomes easier to learn. And our task and our job as theoretician is to do this formally. And along the way, we also build techniques that can parse current or future, let's say, results from classical learning, computational learning theory to an invariant type of results. Okay. So some spoilers. We'll see a very nice and clean applications of these intuitions of things becoming smaller in dimension and thus easier to learn in a certain specific learning theory framework. But for real value functions, things are a bit messier. And this because we know how to deal with different data distributions in Boolean functions, in proving lower bounds of learning Boolean functions, whereas the case is not so easy in the same case not so easy when learning real value functions. Okay, so any questions before we move on to the formalisms of things? Okay. So here, learning under symmetries basically means that the concept class, which is the class your ground truth may come from, is constrained to be invariant under some action of some certain group. And we assume that the ground truth functions come from this more restrictive function class. An example of a learning algorithm would be taken in n samples and then solve the ERM problem, which may in general not take polynomial time, but that's one way to learn the ground truth function. As the spirit of the workshop is there are two types of questions: statistical ones where we ask how many samples information theoretically do we need, and the results are usually in terms of generalization bounds. Versus a computational problem: is there efficient algorithm to do this in terms of time complexity, space complexity, or query complexities? The presentation and the paper will focus more on the second problem, on the second question. Okay. So let's very quickly review pack learning. I know everyone is extremely familiar with pack learning, but let's review it. So we have a set of functions where the ground truth may come from. We call it a concept class. And here we're doing it for Boolean functions. And we also have the distributions over the data sets over the input space, X. So a notation is that if we have a concept or ground truth, C, in the concept class, then we can draw sample from the joint distributions, the subscript C, over this product space, which is a space of samples. Right? So each sample has an input and a label. We also know we also allow our algorithms to make errors, parameterized by epsilon, and we allow it to make more than epsilon errors, but with very small probability, parameterized by delta. So examples would be, for example, adjacency matrix of graphs. And one concept we may want to learn is graph with, for example, with Eulerian cycles. And distributions over graph, for example, would be Arrhenius with a certain edge probability. Right. So an algorithm, so here we deal with a distribution-dependent settings. So the algorithm knows the distribution over the data sets beforehand. We say that it's a pack learning algorithm if it knows all of these parameters. Right? So it knows all the error parameters, tolerance parameters. It knows the concept class as well as the data distribution. At runtime, it's taken m samples, and then it outputs a hypothesis, which is another function that makes large error with small probability. And this is efficient if you need polynomially and many samples, and your A can be evaluated in polynomial time in its input, which is the samples. Okay. So this is a very general framework, captures a lot of algorithms, but it is hard to give lower bound proofs. So often the case you have, like, for example, consistent algorithms, and then if the hypothesis space is small, then you have a packed algorithm. But it's very hard, and it's generally extremely hard to give a lower bound proof that says no packed algorithm can solve a certain problem. So we look at restrictions. Natural restrictions would be statistical queries by Michael Kearns in 1998. And here we don't have access over samples, but over statistics. But we have access to statistics over distribution. What the algorithm is allowed to do is to ask an oracle a query, which is a function over the samples, a bounded function over the samples, and also give the oracle a tolerance parameter tau. In return, the SQ oracle returns the statistics of the function g over the sample distribution within some additive error band specified by tau. So an even more restrictive model of learning is correlational statistical queries, or CSQ in short. And here it put restriction on the type of oracle the type of queries that you can make to the oracle. It has to be of a certain inner product form. So there is an implicit inner product structure in your space of labels, and this is called a correlational queries, because the statistics over this type of queries is in the form of a correlation between your query function f and the ground truth C, ground truth concept C. Okay. So we have defined pack, we have defined SQ and then CSQ. What if CSQ is too restrictive? Okay, but first we have to define the hardness of learning in the CSQ or SQ model. And here is in terms of query complexity. So a class of function is hard to learn if any algorithm that gives good answers up to some accuracy epsilon only makes polynomially many queries to the oracles with tolerance not too small. So CSQ models, although it's restrictive, it still captures certain interesting algorithms that we care about in practice. For instance, population gradient descent under square laws with some additive noise at each descent step can be captured by CSQ. And this comes from a straightforward computation. For example, if you want to run one step of gradient descent, full batch gradient descent, if you know the population distributions, you are going to compute these entries to the left, on the left-hand side. And with mal-assumptions on the data distributions, you can pass the gradient inside the expectations, and then do the usual calculus. You in a product these in a function with its own gradient, and what you get are the two terms on the right-hand side, on the left-hand side. So the first term here is independent of y. So as recall, the CSQ model or the SQ model, only the complexity comes in terms of query complexity, so you can take your time and compute this. The second part, which does involve a y, so it does involve the unknown ground truth label, appears in the form of correlation values. So you can put this into CSQ oracle, and it will give you an answer up to some additive error. And the Gaussian noise, so the distribution of the noise will depend on the distribution of your over the input space. But adding some kind of noise will counteract the errors, the errors controlled by tau in the CSQ oracle. And you can have a coupling arguments between each step of making a query to CSQ oracle and each gradient descent step under this model. So it is not hard to see that there's an inclusion. One is a restriction. One learning framework is a restriction of another. For example, you can simulate statistics just by observing samples and then do a Hoeffding-Bound. But whether this is tight or not is we now answer. So there is an exponential separation between SQ and PAC. This comes from learning the concept class known as parity. Parity is a set of functions indexed by C. C is a subset of the set 1, 2, 3 over to D. And given an input Z, the function looks at the values of Z at index enumerated by C, and then just count the number of -1, whether it's even or odd. And this is over the uniform distributions over the hypercube. For value functions, it's known that CSQ and SQ is the same thing. You can simulate any SQ oracles with a constant number of queries to the CSQ oracle for Boolean functions. And for real value functions, there is an exponential separation between CSQ and SQ for learning sparse polynomial over product distributions. And this is work done by Andoni, Panigrahi, Valiant, and Zhang in 2013. So we have described all the models and have seen some kind of properties between them, three different models. What are some of the tools that we can use to, let's say, prove lower bounds? No CSQ algorithms can learn a certain concept class, let's say. And here I'll describe what is known as CSQ dimension. This is not the exact same dimension we use in the paper, but this is good for building intuition without being too complicated. And it's the maximum number of functions in your concept class that is pairwise almost orthogonal. Right? So you find the largest subset F such that every distinct pair of functions, the correlation is small, and you cannot cheat by making the norm goes to 0. The norm must be bounded away from 0, so that the small correlation actually makes geometric sense. You compare this to VG dimension, which is the notion of dimension in PAC learning. VG dimension is a more combinatorial quantity, and this is to me at least, this is a more geometric quantity, and it gives some kind of orthogonality in the space of functions that we are interested in. And to close the loop, there is a mechanism to go from a bound on CSQ dimension to query complexity in the CSQ model by Blum-First, Jackson, Kearns, Mansur, and Rudik in 1994. That says that if you have this CSQ dimension of this many, then proportionally you must make also at least that number of queries. And a short hand-wavy proof for this is that the best, the most informative answer you can get from a CSQ oracle is a correlation value of 0, and that will eliminate a certain subspace of the function. And if your space has this many things you need to eliminate, then you need roughly this much calls to get the correct function. Okay, and so this suggests a proof, an attack kind of strategy that goes into your set of your concept class and find a large family of non-vanishing hard functions that are pairwise almost orthogonal. And this paved the ways for many CSQ lower bounds for for one hidden layer neural networks, let's say, in the general setting, non-invariant setting. Okay, so that's the formalisms. Now we present the result that we showed in the paper. And for general Boolean functions, the takeaway is that there is an intuitive extension of existing lower bound techniques that will give us a very, very clean answer. Here, again, we're looking at the hypercubes as the input space, and our group will partition X into orbits. So orbits is a fancy name for the equivalence classes that are the things that contains things that are the same, that are equivalent under this action. And we collect the probability of a random bit string falling into some of these orbits into a vector of size k, that's PO. So for example, the first entry here would just be the size of O1 divided by 2 to the n. It's proportional to the size of each orbit, if this is uniformly random. And we are interested in general Boolean invariant functions. So we're interested in all Boolean functions that with this particular symmetry. And we have just stated the main result now, and that's if any SQ algorithm that learns the invariant Boolean class of functions up to small classification error, some constant less than 1/4, with a certain tolerance, requires at least a number of queries that's proportional to the inverse square of the 2 norm of this probability vector. And intuitively, this makes sense because, as mentioned, if you are restricting to an invariant function class, then the set of orbits is the effective domain. And a uniform distribution over X induces the distribution over this new smaller effective domain that is captured by the probability queries. So now we can just invoke existing techniques in SQ lower bounds for learning over a distribution that is other than uniform distribution specified by PO. Before we go into the spoof sketch, let's parse this a bit more so that it's a bit easier to read. And you can use Holder inequality to take this squared norm term and bound it with the maximum orbit size. And with this, we have applications to certain groups that are used in practice. For example, a symmetric group. So for symmetric groups on n bits, the symmetries is large enough that the query complexity becomes polynomial. So if you remember, parities force the usual query complexities in learning Boolean functions to be exponential. Here, the symmetry group is large enough that this become a polynomial. However, for graphs and cyclic groups, the symmetry group is not large enough, and you still result in a exponential bound, but there are quantitative chipping off in the lower bound. And in summary, it is clear that for symmetric Boolean function classes, there's a reduction in some kind of dimension, and it chips off the existing SQ lower bounds. As for the proof techniques, we make use of a notion coming from the appendix of these incredible papers by Chen, Golagota, Cleveland, and Mecca, harness of noise-free learning for 200-layer neural networks of an pairwise independent function class. This is the full definitions, but roughly speaking, if you draw X and X prime from the input distribution and draw F uniformly from the concept class, and you form this pair, the pair should look uniformly random with certain probability 1/eta. And with this comes a mechanism that translates a pairwise independent function class to a lower bound on the number of queries to an SQ oracle in terms of the probability that of this drawing become uniformly random. And for us, we can check that eta is equals to the square norm of the probability vectors over the orbits. Okay. And so that's the result for general Boolean functions. What about still Boolean functions but smaller class, right? More practical invariants? And for graph learning, there is a notion of graph neural networks that may capture something smaller but still practical. And in this section, we'll show that even practical GNN stands for graph neural networks. GNN realizable Boolean functions are still hard to learn. And we haven't defined GNN yet, but anything that fits into these definitions can roughly be called GNNs. You have input, an adjacency matrix, and your function is constrained to output the same thing when you permute rows and columns with the same permutation. Okay, so anything that satisfies this constraint can be called a GNN. Well, it has to have some neural networks component to it too. An example is message passing neural networks, which I won't define very concretely, but what's happening is that you start, each node has a color, that's a start. In the first layer, each node looks at its neighbor and then aggregate the color of the neighbors. Right? So it can sum the colors, it can take the maximum of the colors, whatever, and then it updates its own color based on the aggregated colors of the neighbors. And doing so would result in this invariant constraint being satisfied. Another example would be graph convolutional networks, which we will not describe here, but it will show up a bit later. So we'll postpone the description of GCN to a later slide. And the concept class, the small concept class that we are trying to learn here is going to be two hidden layer GNNs, with the first layer being a message passing layer. So an input, again, is an adjacency matrix. You start with each node having trivial color of all 1, then you aggregate it, then you then you add some learnable parameters B, and then add a bias term, which is also learnable A. You put a nonlinearity on it, and then you sum everything up. So the summation will make it node permutation invariant, and all these are usual neural network business. The second layer is a one hidden layer rail networks with K2 hidden neurons. And distributions will be uniformly random over the hypercubes that's present or absent of edges, or equivalently is Arrowstrandy with edge probability half. And here we assume that the number of hidden neurons, both in the first and second layers, is of linear order. And an important thing to note is that unlike general one hidden layer neural networks, which is universal, it can approximate any functions, this message passing is not universal. So there are functions, there are graph invariant functions that it cannot even approximate, even if you let the number of layers goes to infinity. So this is a strictly smaller class of Boolean graph invariant functions. And okay, so our proof, the attack strategy is going into this family of functions and find something that is hard. And our constructions have this notation CAI. A is the adjacency matrix of a graphs, counts the number of nodes without degree I, and so I can range from 0 to n. And we define hard functions that is indexed by a subset of the set 0, 1, 2, 3, all the way to n, and a bit b. So we just add b into something that looks like a parity functions that counts the number of nodes without degree I for I being specified by the subset S, and then add them up mod 2 to make it Boolean. And for the family of hard functions, we just go on and collect all of these hard functions, which there should be exponentially many of them because we take any subset of the set 0 to n, and also any bits b 0, 1. So shout out to Bobak, who came up with this proof, as well as a majority of the proof that you also see in the last general Boolean section. Okay, so the main results we let's state it first is that any SQL algorithm that learns this class, the two-layer hidden message passing neural networks class, up to small classification error constant less than 1/4, with certain tolerance, requires at least exponentially many queries. And the conclusion, the takeaway here is that even the smaller class of just message passing, which is not universal, doesn't cover the whole set of invariant Boolean graph functions, is still hard to learn. Okay, so that's with the Boolean cases. Now we deal with real value GNNs, and here the result is going to be not as nice, not as comprehensive, not as total, but we can still say something about lower bounds in terms of CSQ in the CSQ model. And here we're going to show hardness of learning GNN in feature dimension. So I haven't defined what's feature dimension, which I'm going to do now. So the previous version of GNN only has input a graph, like an adjacency matrix. Here we also have node features. So if this is, for example, a social network graph, then the node features will be your date of birth, your names, your hobbies, your likes, and your posts, etc. And here for simplicity, and that's probably most of the things we know how to do, is to assume that the features here are ID Gaussian. And the graph distribution can be quite arbitrary as long as it's assigned at least a constant probability to non-degenerate graph, to non-empty graphs. And we consider this class of function, which is a bit intimidating, but let's go through it slowly. Let's look at the input. There are two inputs. The first one is a matrix, a data matrix of size n to the d, and here's the number of nodes in the graphs. And d will be the feature, the number of features. So that's the feature dimension. This is the hardness parameter that we want to scale, and we assume n to be constant with respect to d. We also have input a graph. We also have as input a graph, which comes up as an adjacency matrix in the function definition. What the function is going to do is that it's first going to apply this adjacency matrix to the left of x, to the right of x. And what this does is that it sums up the neighbor features. So each row of x has n rows. Each row is a vector of size d. And what this multiplication does is that each node looks at its neighbor and just sum up the features of the neighbors. So these steps inform the model of the graph structure of the data. Then we do our usual neural network business, applying a linear map to the resulting aggregated node features, and then apply a nonlinearity, which is ReLU, and then another layer. And so here, all the yellow things are learnable weights. Yes?
Is this like one hidden layer? If I think of like AX as the input, so this is a one hidden layer neural network? Or?
Right, it's one hidden layer graph convolutional network, yes. It's one hidden layer because there's one, so yeah, so the exact name I don't think is that important, but this is the exact class of architectures that we want to capture.
Is it symmetric though? It's not symmetric with vertices, right? Because the weight vector W, it can change the weight of individual vertices, right?
Okay, so it can so at the end of this step you have a vector of size. You have a matrix of size n to the r to the n times d, and then you apply W to the right, which apply W to each of the rows. Each of the rows correspond to each of the nodes, and it's invariant because here you have a sum over the nodes. Yeah, good, great questions. Okay, so this is the large class that we assume our ground truth comes from, the concept class. And the attack plan again is to find a hard functions within the set of hard functions within this set, and this is based on a extremely nice paper by Nicolas, Kane, Cotonis, and Zarifis showing exponential SQ lower bounds for learning one hidden layer ReLU network. So this is the usual non-invariant one hidden layer ReLU networks. So here the hard functions are indexed by this B matrix, which is a low dimensional projections from R to the D, which is the space of features, to R2. So here Fn is a hard GNN in low dimensions. So what happens here, let's go through it step by step, is that first we applied the projections to the right of x, which transform each row. So each row corresponds to the feature vectors. It projects each of the feature vectors in each node down to a low dimension of R2. Then we applied a neural network, a graph neural network in the low dimensions, in the space of low dimension features that look something like this, with special weights W star and A star coming from Diaconus Kane, Canonis, Zarifis paper. Right. So with a concentration bound, you can show that there are exponentially many different low-dimensional projections, and the task and one can prove that these functions, when defined like this, is roughly almost pairwise orthogonal for different projections B. Okay. So let's state our results first. Basically, if you let the feature dimension scales, and this is the complexity parameters, you let everything else fixed, and the number of hidden neurons is linear in D, then any CSQ algorithm that learns this hard class up to some errors requires exponentially many queries, or some query with exponentially small tolerance, which is not allowed in the efficient learning framework of CSQ. And the main new tool that we introduced here is a graph invariance version of Hermite polynomials. So Hermite polynomials forms an orthonormal basis when you normalize it properly. It forms an orthonormal basis of correlations when the data distribution is Gaussian. So this is the usual multi-index Hermite polynomials. We can symmetrize it, make it invariant to graph actions by having an input x here, apply the adjacency or Laplacian matrix to the left of x, and this will aggregate the features in x. We look at individual nodes, aggregated nodes, applied the Hermite polynomials to each of the nodes, and then sum it up to make it invariant with the correct scaling to make it orthonormal. And this turns out to also be an orthonormal basis for one hidden layer GNN, which we defined just now, with respect to the L2 inner product with respect to the Gaussian distribution. And this works out because the action of the graph is diagonal to the actions of the weight matrix. So what I mean by that is that here you have this is our inductive bias. This is the thing that we want to symmetrize over. And this is the weight matrix, and they are on different side of the input of the things that we are trying to show hardness on. They are on different side. Later on, we see something that's on the same side, and that causes a lot of troubles. This also means that you can aggregate the features first and then apply the weight matrix, or apply weight matrix first and then aggregate node features. It's commutative in that sense. It doesn't matter which one you do first. Okay. So that's for graphs. What about other symmetries? And here things become much more complicated, and we will take a look at some hints of why things become much more complicated in the graph setting. So a naive approach to symmetrizing any function is through group averaging, which given a group, you can just sum over the evaluations at all the orbits. So this is obviously symmetric with respect to the group G. So what will happen if you symmetrize a one hidden layer neural network? You get something like this. So you're summing over you're summing over orbits, elements in the orbits of your input x. And here, if you notice how inductive bias, the action of G is on the same side as the weight matrix W, and that will complicate the proofs later on. Okay, so an example is that if D is equal to 1, each item has only one feature, and G is a cyclic group, and this captures convolutional neural networks with very large filter, and that loops around. So for each element of the cyclic group, you just shift x cyclically by 1, and that's something like a CNN. Okay, so again, we prove exponential lower bound of CSQ in the CSQ framework by using subspace enumeration from the diagonal class K, cotonis, and Zarifis, with our hard functions having input also a matrix of size r to the n. Here you have n items, so let's think of this as point clouds. So n here is the number of points in the point clouds. D is the coordinates of the point, so D is fixed, and the number of elements is the hardness parameters that we're going to scale. And what the function does is, and then for our hard functions, we still use orthogonal projections to project the input elements in the orbits of the input to a low-dimensional subspace before applying a stock hard functions that is constructed using similar special weights from diagonal class K and cotonis and Zarifis. And the scaling is to make sure that the norms goes to 0 as G increases with n. And again, one can form a sort of concentration result that says that there are exponentially many such subspace dimensions that make all of this pairwise orthogonal. And the fact that the weight matrix is on the same side as G will complicate the proof of lower bound of norm lower bounds, make sure that these functions do not vanish in norm. So our result states that if you let n scales, so this is the complexity parameters, then there's a set of projections of at least this size, such that any CSQ algorithm that learns up to some constant errors requires this much queries. And when G, the size of G is polynomial in n, and then this is an exponential lower bound. So it makes sense to assume that the size of G is polynomial, because if it's exponential, just evaluating the group averaging naively would require exponential time. So we wouldn't want to do that. We can do something else when the size of the group is large, which is called frame averaging. And for example, a very nice example is if you have the symmetric group, then the size is 2 to the n, there are 2 to the n permutations. But you can symmetrize it just by first sort the input and then put it through a neural networks. And this is obviously invariant to permutations of the input vector. So frame averaging is sort of like a minimal generalization of this canonicalization idea, assigns each point in the inputs with a set of group transformations such that averaging over these transformations only suffices to make the function symmetric. So here you can think of this frame in this example is just assigning each input with the permutation that's sorted. And then you only have to evaluate one group transformation. And of course, you can also make the frames to be the whole group, and it goes back to the group averaging case. So what happens when you frame average one hidden LLPs is that you get the exact same form as group averaging, but now you just need to sum over the frames. It becomes a lot harder. So let's look at this for one particular frame, the frame of sorting that we just described. When these go to 1, and we just sort the input vector, and then we go through the usual neural network business of linear, nonlinearities, linear. So if x, even if x is Gaussian, this sorted random variable has a very complicated distributions. So proving CSQ lower bound of this is equivalent to proving CSQ lower bound of one hidden layer neural networks, but with a new complicated distributions, which we don't know how to do. And the usual frameworks of diagonal class K and cotonis no longer works. At least we don't know how to make it work. If you do know, please let us know. And the short solution is that we assume something else. Additionally, we assume sign invariance of the frame. So instead of just sorting, we sort by absolute values. And then we prove a super polynomial lower bound for CSQ using hard functions from Goals, Golagota, Jin, Kamaka, and Clivens. And there are some other results that doesn't fit into the time frame of the talk, so I'll just state them here. We also have a SQ versus CSQ separation for learning invariant polynomial, sparse invariant polynomials. This generalizes Adoni's result of SQ versus CSQ for learning sparse polynomial. We also show NP hardness of proper learning of GNNs where hardness of learning half space with noise. And of course, with all these CSQ, with all these hard functions, we have to prove that the L2 norm doesn't vanish. Right? So in conclusion, we formalized the intuition that by putting a restriction, a symmetry restriction onto the function class, you make it smaller, and thus there's some quantitative chipping off of existing lower bounds in the SQ and CSQ settings. We gave SQ lower bounds for Boolean functions, for general Boolean invariant functions, as well as a smaller graph invariant function set. We also gave CSQ exponential CSQ lower bounds for real value functions, includes one hidden layer, GCN, and group averaging, and super polynomial lower bounds in the CSQ model for real value sign variant frame average, one hidden layer MLP. And along the way, there are tools that may be of independent interest. So that concludes my presentation. The paper is online on arXiv together with the contact information. So feel free to send us an email or chat with us after the talk. We'd love to answer all questions and hear all comments. And once again, shout out to my co-authors, Bobak, Hannah, Stephanie, and Melanie, without whom this paper would not be possible. Yeah, thank you.